Okay, last lecture we ended by basically coming up with the most simple version of a geoacoustic inversion, where we scattered a plane wave off the bottom and said, hey, look, it depends on the reflection coefficient of the bottom, and from that we can determine some properties of the sediment. We were a little bit vague there, but we talked about density and sound speed. Take it for granted that we can relate those to grain size and other material properties of bulk material properties of the sediment. So let's talk about the surface now. And we actually did come up with a solution for the surface some lectures ago. So we had the soft, right? We had this soft sea surface, I called it, which is a bit misleading, I think, but you gotta say something. Where we had the reflection coefficient was equal to -1. So essentially we're saying the sea surface is like a perfect mirror, acoustic mirror that inverts the phase of the image. Okay, so let's look at this a little more in the context of how we looked at the bottom, right? So let's write our full field solution, right? Full field solution for source near the surface. Okay, so here's our surface. It's pretty flat, I guess. We're gonna call this medium 1 now, this medium 2. Just flip it from the bottom. We're gonna have our incident wave, reflected wave. It's got an incident wave number, K prime. Reflected. We'll say this is going to be the incident angle, reflected angle. We know they're the same. And okay, let's write the solution here. So we know in region 1, P in two-dimensional xz here, we're going to have e to the I k dot x, and then we're simply just going to have minus, right, e to the I k prime, which is the same as k, x, right? So essentially saying, okay, we have a plane wave coming in, we have a plane wave coming out. So we can simply just write, the reflected amplitude here being the -1, giving us a negative sign. And that just gives us a very simple equation for what this looks like. So what are we actually seeing here? Well, it's very tempting to simply continue these plane waves into region 2 and say, we have a mirror image. So the incident reflected waves are mirrored images. Okay. Now that's a very simple solution. It's just a plane wave solution. Let's consider a real source. And that's going to, push our theoretical abilities a little bit more. So let's consider a real source, not just some plane waves. So now our setup is we're going to have this slightly tilted sea surface, right? And we're going to, let's be specific here. We're saying P equals 0 on the air side. And on the water side, we're going to place a source. We're going to place a receiver, some R and Z, X and Z if you prefer. Source. And we can consider multiple paths, a direct path, for instance, of travel, a reflected path here. We will call that, I don't know, R not prime. And we want to come up with some sort of theoretical framework to do this. Of course, here we don't have a plane wave, so we need to deal with our source. How do we do that? Okay. Well, there's one simple truism in acoustics. Just write down the wave equation. So let's add a source to wave equation. And pretty much all problems, if you can write down the wave equation, solve the equation, then you have the solution to the problem. So very, very fundamental idea here. Okay, so we're going to say our source is going to be f of x t, okay? Some functional form in time and space. So just note, time is in there, space is in there, right? And so this is going to look like, well, I know you're screaming it out at home. You can't resist. We got a inhomogeneous sound speed, and then the time derivative of the pressure term. And now instead of 0 on the right-hand side, I'm going to put a 4 pi f of x t. Okay, so there's our source term. Okay, so before, we already had f of x t equals 0, and that gave us the homogeneous wave equation. And we found the solutions to those, right? So we know that, okay, there's going to be some usefulness with those homogeneous solutions. So how can we, how did we approach this when it was the homogeneous equation? Well, we actually transformed this right to the Helmholtz equation, right? So we need to assume harmonic time dependence of f of our source term. So assuming harmonic time dependence, then big scripted f there, which of course is our Fourier transform of big F, our source, is going to be equal to f of x omega. And of course we know this is a very safe assumption because of Fourier series and the fact that we can decompose any function into a series of harmonic functions. So we're good. We're good. So what does this give us? What does the Helmholtz equation look like with a source? Well, we got our Laplacian, we got our k squared. We still have an inhomogeneous k. Here's our p in terms of omega. And now we have little f of x omega. Great. Okay. So let's just clarify a few things about f. And when I say f, I mean big source f or little source f. How do we write f or f in a convenient way? Well, convenient and true. We want it to be representative of reality. So one of the easiest things to do is say, let's say we have a stationary, right? So that's going to take care of our space aspect, point source. Okay? So that would mean that f of x omega is equal to a delta function. I'm going to say xs is the source position. Oh, sorry. I'm going to say x naught is the source position. That's a little bit better. And x is the two-dimensional space we're working in. So now we're going to have, this is equal to x naught minus y naught, for example. Could be z and r. Okay, being a bit hand-wavy, but you know what I mean. So let's recall a few things about delta functions that are handy. So recall x naught, the definition. It means it's 0 for x not equal to x naught and is equal to infinity when x is equal to x naught. And so the most familiar, I'm sure, form in the 1D here, this big peak, which I've already given, mistakenly given some width. This should have infinitesimal width, infinite peak. And that combination is such that if you take the volume integral over the three-dimensional function, you get 1. Or simply the integral, the one-dimensional integral over the one-dimensional function, etc. So this has some extremely useful properties in the Fourier transform, in the sense that if you take the integral of gx, let's do this in 1D, over whatever limits straddle x naught dx, you just end up with the function evaluated at x naught. There's also a few nice definitions. We can say that delta x equals the limit as a tends to infinity of sine ax over pi x, very useful, and is equal to the limit as a tends to infinity of 1 over 2 pi minus a to a e to the I xt dt. You can see how those might be very useful at some point when we're using Fourier transforms and that form of the Helmholtz equation that we wrote down. So, okay, what does the Helmholtz equation look like here with our Kronecker delta function? So there's our left-hand side, and our right-hand side now minus 4 pi delta x minus x naught. Whoa, I'm running off the board. Okay, so let's say we're in free space now. Space, and we're going to have a homogeneous medium. So in other words, k of x is just going to be simply k. So let me just put that down. K of x just equals k. Then the solution is called the Green's function. And so we can figure out the Green's function for the problem as we have written it, very simply using transforms. Okay, so I'm just gonna say using transforms, and let you work out the rest, maybe in a homework problem or something. Using transforms, ... we can find gx x naught, gx x naught is equal to e to the I k, the absolute value of x minus x naught, over the absolute value of x minus x naught. So this describes the propagation between some point x in the field and x naught where the source is located. And this is in free space, okay? This is in free space. You know what? I'm just going to exploit the technology. Free space. Very important, because we were talking about surface before. Okay. So this describes... propagation between any point x and x naught, where the source is located. And there's something very interesting to notice here. Notice that you can switch the position of x and x naught, okay? Without changing the solution at all. And this is a concept known as reciprocity, okay? So we can write the linearized wave equation obeys oh man, I'm too close to the bottom here. Well, okay. Obeys reciprocity. This is a very simple but very important result, and basically you know, if you can hear your neighbors having a fight, they can hear you having a fight. That's what it comes down to. But essentially saying that propagation from x naught to x is the same as the propagation from x to x naught in terms of amplitude and phase. So very key, important piece of information. So the general strategy here is to use the Green's function, or the solution to this, you know, inhomogeneous Helmholtz equation with the delta function on the right-hand side to satisfy the boundary conditions, okay? So use g from x to x naught to, satisfy BCs by choosing, so what can we choose? Some appropriate form. Oops. So one of these forms I know you've been screaming out since the beginning of class. I'm just going to put such as the method of images. So our problem basically begs it. Okay, so let's return to the source near the surface. Here we have air. We had our source. We had our receiver. And we said, here's R naught. It's going to be the direct path. We've got some reflected path here. We'll call R naught prime the total path length. And we kind of hinted at it. We said, oh, well, let's just place another source here and let this total path length be R1. And, you know, if our original source was at x equals 0, z equals z naught, let's place our new source at x equals 0, z equals minus z naught. Okay? And we have our pressure release surface here, so we know we're talking about air-water interface. And basically we're satisfying the boundary condition here because we know that this source, this image source, and this original source here, our water source, will completely cancel out at z equals 0, halfway between the two sources, and create this boundary P equals 0, which is the boundary condition that we defined as having on the surface, right? We said, well, P equals atmospheric pressure everywhere at the surface. Therefore, it's so small, we're going to call it 0. In terms of a perturbed pressure, okay. So what does our pressure field look like? Okay, we have X. Well, now it's going to be E to the I K R naught over R naught minus E to the I K R1 over R1. So that takes care of these two paths, right? And so the image source represents the reflected path with the sign flipped, and it satisfies that boundary condition. So now let's do just a little bit of regular old geometry to simplify the solution and see, you know, we could plot it as is, but let's see if we can simplify it and learn anything else about it. So how can we write R naught, I should say. R naught is the square root of x squared plus z minus z naught squared. And similarly, R1 is x squared plus z naught squared. Okay. And now we can use the binomial expansion to simplify these a little bit, to bust them out of their square root signs. Just refreshing the memory here. Oops, that's an 8. Etc. And that's, of course, for the absolute value of z less than 1. Okay, so we know that we can always use this here. And we have some certain conditions, right? We're going to have to put on R0 and R1 at some point to satisfy this Z is less than -1, small z. So if we write R0, for example, as this, z minus z0 squared over x0 squared, then we can use the binomial expansion, and we'll just keep the first term, well, the first two terms. Okay, and what is the assumption we've made here? Well, we need this argument. Oh, got to use the tech here. We need this argument to be small, right, in order to satisfy this. So we need the range to be much larger than the depth. And you can, I think it's intuitive that for sources, this works for shallow sources in the ocean. Okay. But of course, we haven't really defined a scale yet. So shallow relative to what? Well, spoiler, wavelength. Okay, and similarly for R1, we can do the same expansion. Let's just jump right to the expanded form here. Now we're going to have a Z plus Z0 over x squared, that's squared. Okay, and then we can continue to expand these, right? We can take an x here. Add some extra terms, or sorry, expand some extra terms out, right? So we can write the cross term here, z times z0 over x, and we're gonna have a minus sign for R0, and for R1, oops, still, we're gonna have the two end terms, and now we're going to have plus the cross term. Okay, and so that's the big difference here, right? You can see that the first two terms are the same, and the cross term is different. So, oops, that tells us that R1 minus R0 is about equal to 2z z0 over x, and R1 plus R0 is about equal to 2x. Okay. Now, new page. Let's keep only the leading terms. So we're going to say 1 over R0 is about equal to 1 over R. It's about equal to 1 over X. And that's, in other words, saying Z0 is much, much less than X, right? Which we said at the beginning. So our method of images solution, combining the two free space Green's functions, looks like P of x is about equal to e to the I kx R0 plus R1 over 2 all over x. And now e to the minus I k R1 minus R0 over 2 minus e to the minus I k R1 minus R0 over 2. So right away there you're seeing, wow, that's so close to the definition of the sine. So you can't help yourself. You have to do it. You say this whole thing is going to be written as sine k z z0 over x, right? So we've used our definition of R1 minus R0 from the previous page. And then we've used the definition of the sine in terms of complex exponentials. And now our first term, we'll just rewrite our first term, e to the I kx over x. Okay? And so what can we tell from this? Well, a whole bunch of things. So this pressure release surface interacts with field significantly. Three exclamation marks, right? So important that I had to write it down. So previously we had this idea of a spherical spreading field. Well, now it's going to fall off, right? With the surface interacting, falls off as 1 over x squared when k, z, z is much smaller than x. So the idea being that when this is a small angle, that's the small angle approximation in sine, right? So in that case, then p of x is just going to become minus 2i. We just take the argument, becomes the function. Oops, getting ahead of myself. So now the important thing is we see that we have an x squared here, right? We have 1 over x squared in the bottom. And so the intensity is going to be proportional to 1 over x to the 4th. And the field is going to have some nulls, right? Right. So this is this tells you how quickly the field goes down, x to the 4. And field has nulls. So this goes to 0, right, when this argument goes to 0. When it goes to 0 or, n pi. When k, z naught over x equals n pi, and let's just call those, let's say x n now, right, because we have a series of ranges where the field is going to go to 0. xn, solve that. Okay, very simple. And lambda, right? And n can equal 0, 1, 2, etc. Right? So we have a whole series of these nulls. So these 2 points here are really going to help us sketch what the field should look like, right? So we have these nulls here. So let's go to a new page and sketch what we think the field should look like from this approximate but useful. Man, oh man. Okay, there we go. Let's write that as the intensity. So we're going to say this is going to be range here, and intensity on the y-axis. So roughly it's going to follow this 1 over range to the 4th line. And I'm going to do this as a log scale. And then we're going to have etc. x1, x2, x3, x4. We're going to have these nulls, which are defined from our previous equation, on the last page or above in the notes. And so you get a mirror pattern here, a fringing pattern, right? And this is called Lloyd's mirror. So fringing pattern. You got to write it with the nice L. Lloyd's mirror. And so there's some practical limitations on when you observe this, right, that have to do with the assumptions we made, right? We had that assumption about the binomial expansion, so we need the argument to be small, so we need the correct ratio between range and depth. And so typically, let's say typically r is less than several kilometers, several km. Z naught is less than hundreds of meters, right? So shallow sources. And F frequency is less than kilohertz type frequency. And of course you need a flat bottom, right? So, or sorry, flat surface in moderately calm seas. That surface gets too rough, Lloyd's mirror tends to go away. Okay. So, what have we accomplished in the last two lectures? We understand the surface effect. We understand the bottom. We know how to add sources and solve our equations. So basically we understand everything about waveguides, but we need to do these things together, right? So there were some conditions we put on there. We said as long as fluid is homogeneous, basically we can solve a waveguide with these boundaries now. So there's our surface, there's our bottom. We're going to have a homogeneous fluid in between the two. Let's say this is R, this is Z, and we have our source. And essentially, we have our receiver. Oops. That's some R and Z. And essentially, we can start to think of all of our problems in terms of, this direct path, surface reflected path, bottom reflected path, surface bottom, right? And how can we deal with these? Well, we can add image sources, right? So we're going to, let's add them in the order. So we'll add our image source here. We'll add our image source here, 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 etc. So method of images provides us with a solution in a realistic waveguide. And essentially, everything is just an exercise in geometry. We can just write everything as a sum, an infinite sum is e to the I k Rn over Rn. And I'll just say solution every time. So that gives us a method to solve all problems in a waveguide. But really, you can see that the geometry becomes pretty untenable. So what we're going to do next time is we're actually going to look at a fluid waveguide and see if we can get a solution that's a little bit less grinding the crank and a little bit more realistic. So thanks for watching.